Hello students, I am Dr. Deepshikha Acharya from Sagar Institute of Research and Technology. In this video I am going to explain about Hall effect. So first of all, let me see the starting of the Hall effect. Hall effect is discovered by the year 1879 by Edwin Hall. This effect is the extension of Lorentz force because it is a combined effect of electric and magnetic field, and the Hall voltage calculated by is given as VH is equals to IB by NQ into W. How this comes, we are going to see in this video. So what is Hall effect? Our basic problem is that. So the Hall effect is a combined effect of electric magnetic field, as I already told you. When a current carrying metal or semiconductor block or a plate is placed in a transverse magnetic field at the right angle to the electric field, a potential difference is developed along the third direction, and this potential is called Hall voltage. And due to this potential, a Hall field is also generated, and this combined effect is called Hall effect. So how it happened, let me see. Because of the application of magnetic field, the current carrying plate have experienced a shifting of charges, and this shifting is along the third direction, and due to this shifting, as we can see in this picture, a potential difference is developed along the third direction, which is the direction of the Hall effect or Hall voltage. So now we come to the derivation of Hall effect. So before to start the derivation, let us see some consideration that the direction of the electric field is X, the direction of the magnetic field is Z, therefore the direction of the desired Hall voltage is the third direction, which is the Y direction. The width of the specimen is W, the thickness of the specimen is D, and the length of the specimen is L. And the charge carriers which are flowing are the electrons. Now, according to the law of conservation of the forces, we can say that for this particular condition, LF, which is Lorentz force, is equals to the Hall force, because Lorentz force is the combined effect of electric and magnetic field. So the value of Lorentz force is minus Q Vx Bz is equals to minus Q into EH. Why this is happening? So as we all know that Lorentz force is equals to Q V B sin theta, but for this condition theta is 90 degree because electric and magnetic fields are perpendicular to each other. Therefore we write LF is equals to minus Q Vx into Bz. X is showing the direction of the electric field for this derivation, and Z is showing the direction of the magnetic field, which I have used in the suffix. Therefore, the value of EH is equals to Vx into Bz. As we know that current density is equals to, and in terms of drift velocity, the current density Jx can be write as minus NQ into Vx. From this equation, we can get the value of drift velocity and substitute this value into equation number 1. So we get the value of EH, which is equals to minus NQ minus 1 by NQ Jx into Bz. Here the value of minus 1 by NQ is equals to RH. It is called Hall coefficient because by this value we can calculate the type of charge carriers, and it is a coefficient because the value of 1 by NQ is always constant for a particular type of material which we are using for the particular Hall effect, this particular specimen. Now we are going to calculate the value of VH. To calculate the value of VH, the Hall voltage, we are using the formula VH is equals to EH into D, electric field into displacement. So the value of electric field we have already calculated is equals to minus 1 by NQ Jx Bz into D, or RH Jx Bz into D. So the value of VH is this. Now we are convert this value into the current voltage equation, because we have always or generally compare electric and voltage current and voltage altogether. Therefore Jx can be written as Ix by A Vz into D, and A is the area cross section, so the value of A is equals to W into D, and so the final VH is equals to RH Ix W into Vz, or we can write minus Ix Bz by NQ W, where I is the current along the x direction, Bz is the magnetic field strength, and number of charge carriers, Q charge on the charge carriers, and W is the width of the specimen, which is the value of the thickness of the material along the direction of the magnetic field. So this is the value of VH. Now let us see some importance of the Hall effect. Hall effect are used to determine the type of charge carriers, as we see that the RH is equals to minus 1 by NQ, and so we can find out the type of charge carriers because of the value of RH. So to calculate the Hall effect parameters, we can calculate the type of charge carriers as well as the type of semiconductors. Number of charge carriers are also can find out by this, and the mobility of charge carriers, conductivity, resistivity are also can calculated by this equation. So we can going to see what is the formula we can get by the Hall effect to calculate the mobility of charge carriers, or we can say it is in the next video I will explain the mobility of charge carriers, how to calculate with the help of Hall effect. Thank you.